Right, material yield or material failure. Now, I need to set up, before we get deeper into this, the difference between ductile and brittle. And so over here, we've got a range from metals that are extremely ductile, or materials that are extremely ductile, to materials that are brittle, and the mode of failure. Here would be a stress-strain curve for a brittle versus a ductile. So something that is ductile has inelastic range to it. Right, where beyond the yield point, we get to a nonlinear relationship and most likely no longer elastic. So the criteria we're going to deal with is for ductile materials. And so you can kind of think of this as an upper limit on the state of stress. So we've dealt with states of stress for quite a while in this class. We've transformed them, we found principles, and so the state of stress is going to relate to an upper limit on its ability for the material to hold that state of stress. And we'll always keep in mind that down in the linear range, even though we're at small strains, we have significant stresses. So keeping something in the elastic or linear range is a small strain problem, but it's a large stress or significant stress issue. Taking a closer look at the failure or the planes of failure for a ductile material versus a brittle material, which has a flat surface, more of a clean break. Here we've got some cup and cone effect, and we will talk about those lines here in just a moment on this ductile material. So classifying something as ductile or brittle depends on several issues. One, it depends on the material itself, but also the temperature. So extreme temperatures, extreme heat, extreme cold have an effect. The most common that you might think of is for glasses. When they are heated up, they go from something very brittle to something extremely ductile at high temperature. It's not just a material issue, but also the rate of loading. So something that is loaded slowly may act in a ductile nature, as opposed to something that is hit with an impactful load may respond in a brittle fashion. It's also going to be the shape or the form of the specimen. So something that may have a shape like this can have a strong stress concentration at that inside corner, so it may end up acting in a more brittle nature right at that stress concentration. And then the other one would be a chemical environment. So the takeaway here is that no single theory can be applied at all times. Again, the criteria we're going to deal with today are for ductile materials, but engineering judgment must be used as to when to apply the theory and the case in which it's going to be applied. There are many yield criteria that can be used, but must be used at the proper time. So we'll explore a ductile material. Here would be a specimen, a uniaxial state of stress. So we've got state of stress where stress is applied along one axis only. And if we go ahead and draw more a circle, we can plot the stress on this face at that point. The other two faces would have zero stress, this one, and then we'd have a plane stress condition, free surface. So if the stress is equal to the yield stress, so you'll see that as a strong capital Y or just with subscript yield on it. So if we look at the Mohr circle, right, the initial state of stress could be rotated up to the max shear stress, and that would go through a distance of 90 degrees on Mohr circle, which would be 50 degrees in real life. And so we're going to spin back to the picture of the yield and this ductile fracture. So this would be all the way out, right? At fracture, we have got a shape that has emerged, and that plane is roughly at about 45 degrees. So for a uniaxial specimen, that would be the plane of maximum shear stress. So back here, 45 degrees in real life would be the transformation from the initial state of stress, uniaxial, to maximum shear. So those lines even have a special name, Luder's lines on mild steel. Those would be the lines of failure or yielding. So at tau max, which would equal sigma yield over 2, this would be the state of stress. So with those lines at 45 degrees, clearly tau max must be important. And we would know that the maximum shear stress relates to sigma yield with a factor of 2. So extending to something that would have more stresses on it, so a beam, and we've got a state of stress that would have both normal stress and shear stress. That can be transformed, right, from an initial state of stress to something that would be biaxial at principle. So that's what we're going to compare this biaxial state of stress back to the uniaxial state of stress. And so we're going to do that by taking the principal stresses and figuring out the radius of the largest circle. So you can take a look at some of this, and what we're going to end up doing is creating failure criterion, which is based on the mechanism of failure, the 45 degrees, which would be the plane of maximum shear stress. So this criteria is going to be founded on calculating the maximum shear stress in a biaxial stress state. So the first criteria is the Tresca, or the maximum shear stress criteria. So plotting here, this is principal 1, sigma 1. This would be sigma 3. And so if the state of stress is inside the yield surface, then the design is safe. If the state of stress has exceeded the yield surface, then yielding is predicted. So this criteria comes down to comparing the radius, or in this case the diameter of the biggest circle. We're comparing that directly to sigma yield. So this surface can be summed up in functional form. So sigma 1 minus sigma 3, diameter of the biggest circle, dipping back to Mohr's circle for 3D stress analysis, and we're going to compare that to sigma yield. So if sigma 1 minus sigma 3 is less than or equal to sigma yield, then no yielding has occurred. So this is why it's called the maximum shear stress criteria, because it's twice tau max is compared to sigma yield. Yield criteria is derived in a slightly different fashion. It's going to be based on the strain energy involved in the deformation. So let's take a look at a triaxial state of stress. So this is in principal orientation with sigma 1, 2, and 3 as noted. I did this in two pieces. One would be a hydrostatic or change in volume with no shape change. So notice we have sigma average, which is going to be on every face. So this is going to cause a volumetric change, but no shape change. Think of that as hydrostatic. And experimental evidence says that materials don't yield based on hydrostatic pressure. So the other piece would be sigma 1, 2, and 3 with sigma average subtracted from each face. And so we're going to superimpose these two answers on top of each other to get the total state of stress. And we're going to look at the energy needed to deform that element right there. We'll compare the energy needed to deform triaxial, and we'll compare it to the uniaxial. And so when the triaxial energy has exceeded the uniaxial, then we will predict that yielding has occurred. So the strain energy involves integrating stresses through strains. So we end up in a linear condition. We end up with 1/2 sigma times epsilon. We can substitute in for epsilon, sigma over E. So 1 over 2E sigma, and we'll go ahead and put yield in there. So that would be the strain energy needed for yielding in a uniaxial state of stress. In triaxial, it's going to be a little more complicated. We're going to have to do that exact same integration in X, Y, and Z. And so at this point, we're just going to start plugging in some expressions. And we'll write one of them out here. So that would be strain in the X direction. That would have to get plugged in there. We would have to do the same thing for epsilon YY and epsilon ZZ. Those would have to be plugged into the expression. So doing the math for you, you end up with the strain energy term that has some sigma squareds in it. X, Y, and Z has the cross terms with Poisson's ratio. And so equating this to the previous picture, sigma XX, we're going to use sigma 1 minus sigma average, sigma YY with sigma 2 minus sigma average, and sigma ZZ with sigma 3 minus sigma average. So also remembering that sigma average is equal to sigma 1 plus sigma 2 plus sigma 3 over 3. And so all those get plugged in everywhere. We get some cross terms that are going to show up. So let's look quickly at sigma XX times sigma YY. That would be sigma 1 times sigma 2 minus sigma 1 times sigma average minus sigma 2 times sigma average plus sigma average squared. And so we've set up all the math. We're not quite going to go all the way through it, but the strain energy in the axial exceeds the strain energy in the 3D. We'd end up with 2 times sigma yield squared greater than sigma 1 minus sigma 2 quantity squared plus sigma 2 minus sigma 3 quantity squared plus sigma 1 minus sigma 3 quantity squared. So that's derived what the von Mises yield criteria looks like. So here would be a picture of it for a plane stress condition. We'd end up with an oval on the principal axes, right, denoted with sigma yield values. So just like for Tresca, if the state of stress principles are inside, it's safe. If it's outside, then yielding has been predicted. Again, this is just a two-dimensional view of it. We have a 3D surface using sigma 1, 2, and 3, but the same concept holds either inside for safe design or outside for yielding predicted. So rearranging that equation, we've got the terms of sigma 1 minus sigma 2 squared. So this is the diameter of one of the circles. Here's the diameter of the other circle and the diameter of the third circle. And so we're going to take those diameters and square them and compare them to 2 sigma yield squared. Right, and again, ordering the principal stresses from sigma 1 being the most tensile to sigma 3 being the least tensile. And in a plane stress problem, one of those would end up being 0. This would compare the two surfaces. So the inside would be Tresca with the hexagonal shape. The oval would be von Mises. So you see that designs, for instance, at that point would be predicted as yielding using Tresca, but would still be safe using von Mises. And so neither one is more right than the other. It's just that this is more conservative. So designs have more the material. We can predict more from the material by using more of the principal stresses. So which one you use is often controlled by the design document or a decision in terms of how safe or how conservative we might want the design to be. So in this class you'll be told which criteria to use, and we'll use both of them. So for these ductile materials and this yield criteria, we're going to try and avoid yielding, and we will use a factor of safety. Sometimes we will apply a factor of safety, other times we will calculate the factor of safety. But in general, the calculated stress needs to be less than or equal to some allowable stress. And the way we're going to calculate the allowable stress is either off the ultimate stress or off the yield stress. Factors of safety could be applied to either. So for instance, this top one would tell us that sigma allowable would be equal to sigma ultimate divided by some factor of safety. So we're going to use a fraction of the ultimate to create an allowable design, an allowable stress to design to. So for our yield criteria, this is going to work in a very similar fashion. So there's the Tresca yield surface, and the factor of safety is going to be calculated by the capacity, sigma yield, divided by the demand, which is sigma 1 minus sigma 3. It's also sometimes written as 2 tau max, twice the radius of the largest circle. So here we would be able to create a limit for sigma 1 minus sigma 3 using the factor of safety from the yield stress. So von Mises is a little more complicated. We have an equation that obviously involves more principal stresses, but it has a sigma yield squared in it. So for a factor of safety, the calculation becomes sigma yield divided by, you can kind of think of it this way, we take this to the other side. We're going to then have left over on the left side this quantity in the red brackets. So we're going to divide it by 2, so there's the multiplication by 1/2. We're going to have to take the square root of both sides. So it's a little bit of an involved calculation, but all it is that quantity right there, right? The diameter squared of all 3 circles. We're going to take that quantity, multiply by 1/2, and then take the square root of the entire quantity. That becomes the calculation of the demand on the system that we can compare to sigma yield. So again, sometimes we will apply a known factor of safety, or we will calculate the factor of safety if yielding has not occurred. So That equation perhaps won't be as intimidating when we end up with a plane stress problem because we know at least one of those is going to be equal to 0, so it simplifies a little bit.